The last type of muscle we want to talk about is the one called cardiac muscle. So remember we had skeletal muscle. We gave the best way to think of it is think of the gastrocnemius as a great example. But of course, remember there's 657 skeletal muscles in the body. We talked about smooth muscle. I gave you examples of the uterus, examples of the bladder, examples of blood vessels. A lot of places, the intestines, the large intestine, small intestine. Those are all smooth muscle, the bladder. But now we want to think of the most organized muscle in the body. That will be a separate topic in anatomy and physiology, cardiac physiology. But to understand cardiac physiology, when we get to it, we need to understand that third type of muscle called cardiac muscle. Remember, cardiac muscle is striated, so it's very organized or striped appearance under an electron microscope. And because I can't tell my heart what to do, it's called involuntary. And so when I think of cardiac muscle, I'm going to remember it's the most organized of the three types of muscle. It's going to have the highest oxygen demand. It's also going to have 1 to 2 nuclei per cell. So remember we said smooth muscle's got 1 nucleus per cell, and skeletal muscle's got 100 to 1,000 nuclei per cell. This is only going to have 1 or 2 nuclei per cell. So again, when I talked about functional units, remember I said that everything in the anatomy has some type of functional unit. A few minutes ago I said the functional unit of smooth muscle is organized actin and myosin. So it's not that well organized. I cannot tell it what to do, and I couldn't, even if I could, it would not be able to move just like I can move my finger an eighth of an inch. I could not tell something in my intestine to move an eighth of an inch. I know that I've got a function unit of skeletal muscle. And I said that's going to be called a sarcomere. And then I've got the last one, which is going to be cardiac muscle. And cardiac muscle function unit is going to be the sarcomere plus a structure called an ICD. And an ICD stands for intercalated disc. We want to memorize this definition now in muscle, and at the same time we want to know it and memorize when we get to the heart. An intercalated disc is going to be defined as a structure that electrically couples adjacent cardiac muscle cells, fibers, myocytes. So it's going to join together each of those individual muscle cells and allow the heart to beat as one big structure. So when you go into the book and learn about anatomy and the different things and read the chapters, you'll see that, I'll just point one out to you very quickly here. And if you go to your textbook and you said out, I'll just pull the page here for you. And let's see, it's actually right here. So when you go to page 128 of your textbook, you're going to see something called the sliding filament theory of muscle contraction. That is what I would really call microscopic anatomy. These are structures that I could not see with my eye alone. I would have to have an electron microscope to see these. And I try and really simplify this and do that by showing it in just very tiny structures. But if you just kind of walk your way through this as you read the book, because this can be very easy or very, very complicated. So as I look at this, I notice that I've got a line here coming down straight, kind of a vertical line. I got a vertical line here. Looks like there's one that's kind of dividing it down the midline. Okay? And so if I just try and say, well, how do I remember this? How do I get the big picture of how this is really going to work? And so after I read the book and looked at that figure of 128, I basically could say, well, if I took a structure called a sarcomere, because remember I said that the functional unit of skeletal muscle was a sarcomere, and the functional unit of cardiac muscle is a sarcomere plus an ICD. If I'm able to draw a sarcomere and understand it, all I have to do is add one little structure called an ICD to it, and I can understand cardiac muscle. So this structure here, as I'm looking at, and again, just oversimplifying what's already simplified in the book, this is going to be called a Z line. That's a Z line, and that's a Z. So always write down Z line. Remember, Z line is going to be the beginning or the end of a sarcomere. So from here to here is the sarcomere. And as I look at this, it looks to me kind of like a Roman numeral 1, and therefore I'm going to write on the top of this A, and I'm going to write on the top of this A. And then I'm going to run a line down the middle of this here, a horizontal line, just like in the textbook. If you notice, I've got this horizontal line running this direction. I've got these vertical lines in this direction. So this is actin and this is M. This is myosin. So A equals actin equals a thin, light protein, CHOM, remembers the acronym, myo for muscle, filament. And it's going to be called light or thin is because when you, in organic chemistry, you understand what's called what rotates plane polarized light. And the way that actin rotates plane polarized light shows on an electron microscope a very light structure, and therefore that's where it got its name of the A band or the thin light protein myofilament. And then I've got my M, and remember M is going to be myosin, and myosin is going to be a thick, dark protein myofilament. So therefore the same thing, the way it rotates plane polarized light, myosin is going to have that dark appearance. If you kind of think now, that's where that term comes in of striated or striped. Kind of think of a zebra's got light bands and dark bands. Sure enough, there we are with this. Muscle under an electron microscope has got light bands and dark bands, and those bands are going to come into play by the way the organization of the actin and the myosin. And then if you notice again, looking at the diagram on page 128, you'll see that I've got a line coming down the middle. So I'm just going to really simplify this and put a lowercase m up here. And the lowercase m is going to stand for, let me just kind of fix this so I can have you able to see it. There we go. So that lowercase m is going to be the midpoint of the sarcomere. And then if you notice that I've got to figure out how in the world am I going to get muscle to contract. And somehow, if you kind of think of, I always think of my fingers, how they interdigitate. And so if these are my two thumbs, and I want these thumbs together, and if these are actin and these are myosin, if I interdigitate my fingers together, my thumbs start coming together. And I'll just show you another way to look at it. If this is my two lines here, so there's my Z line and there's my Z line. And if you notice, there's got a transverse line here. I notice there's something that's coming down in this direction, okay? And that's going to be a cross bridge. So therefore, between the actin and myosin is going to be a bridge. And it's going to be able to bring things together. And again, I'm oversimplifying. But again, if I look at this drawing here and say, well, here's this Z line and here's this Z line, and I want, in order for this muscle to contract, I want these two pens to come together. And the only way I can do that is I've got to take this Z line here. So we're going to just memorize and say this is called a Z line. And what I'm going to do is I'm going to pull at that Z line. And if I pull from the myosin pulling at the actin, these two pens are going to come together. And as they come together, the muscle is going to contract. Now, there's an area here, if you notice, that if I put this pen right here, and I put the other pen right here, just so you can kind of think of the big picture. And if you notice I have these two pens here, what do you see? I only see what? Myosin. I don't see any actin at all between these two pens. I see there's actin there, but I see in the middle is M or myosin. So therefore, this is called the H zone. It's only myosin. And so therefore, when a muscle contracts, the H zone gets smaller. So this area between here and here is called the H zone. And the H zone is only going to be myosin. It's the darkest band inside of a sarcomere, okay? Now, again, just to simplify this, if I look at this again, this very basic drawing, if I take this pen and lay it right here, and I take this pen and lay it here, I notice that there's a region here that looks to me like I see a lot of actin, because I see actin all the way across here, all the way across here, and I see a little myosin sneaking in here. So that area that I'm looking at here that's got a lot of actin and a little bit of myosin is going to be the I band. And the easy way to remember that is I. This looks like a capital I, a lower uppercase I. Look at the uppercase I. There's the top of the I, the bottom of the I, and the middle portion. So just think of this I band, which is right here, is comprised mainly of actin with some myosin. So it's going to be a fairly light band, okay? That's how you want to look at that, all right? And then, of course, you're going to have an area that's going to have what's called an I band. An A band. And so an A band is going to be a lot of myosin and a little bit of actin. So how would I find that? Well, right here. if I take and put these two pens right here and see what do I have, I've got a lot of myosin, I've got a little bit of actin, and therefore that's going to be called the A band, okay? So just think, if you kind of slowly walk your way, this diagram is fairly simple, but if you just kind of look at it and picture what I've just told you, you'll see how just take a couple of pens and lay them down, and you'll see how you're able to understand what's called the sliding filament theory of muscle contraction. And all that's really telling you is that every time I exercise, I break a cross bridge. I'll give you an example. You went to the gym. You noticed on the wall it says you can buy the new protein shake for $6.95 for the 14 ounce, and you bought one. And the first question I'd ask you, is it contain protein? And the answer is no. There's really no protein in that protein shake. What you have are amino acids: valine, leucine, isoleucine, threonine, alanine, tryptophan. Those are amino acids. Amino acids are the building blocks of proteins. So when I buy a protein shake, or you buy a canister of what's called a muscle builder, all you're buying are amino acids, and you're going to take and by anabolism, you're going to build up proteins by taking long chain amino acids and adding them together. That's why you always see that the classic statement is that amino acid is the building block of protein. So you'll always see an AA, an amino acid, equals the building block of protein, CHON. So you're not really, as I say, buying a protein shake, you're buying an amino acid shake. The last thing I really want to talk about here is that since I've drawn what's called the sliding filament theory and talked about the sarcomere, I want to just talk about cardiac muscle, which I began by talking about. And just remember that all I have to do to change this skeletal muscle diagram into a piece of cardiac muscle is I'm just going to draw really three of these, looks like uppercase I's. And I'm going to kind of just show that I've got myosin sitting here. So remember, this is A for actin, M for myosin, A for actin, M for myosin, A for actin, M for myosin. I'm going to have a cross bridge here. I'm going to have a cross bridge here. I'm going to have another cross bridge coming over here. The difference between this piece of skeletal muscle I'm looking at right now, if I wanted to turn that into cardiac muscle, remember I said, what's the function of cardiac muscle? It's a sarcomere plus an ICD, an intercalated disc. Remember I said an intercalated disc is an electrically coupled adjacent cardiac muscle cells, fibers, myocytes. So therefore, if I put a squiggly line over the top of this Z line here, here's a Z, there's a Z, there's a Z. I don't see it over the top of every Z line. I only see it between adjacent cells. So therefore, if I drew a line that stopped here, and I drew a line that started here, right here where I see this squiggly line, that was either the end of a cardiac cell or a cardiac myocyte, but at the same time, it was also the beginning of another one. And so it's that intercalated disc that allows my heart muscle to beat as one big muscle. You know, when I sit here and say I want to lift this cup that's sitting right here, well, I know that cup at the most could weigh 16 or 20 ounces. So my body's just going to recruit a certain amount of weight and say, I only need a few fibers or bundles to lift 22 ounces. My heart does not work that way. My heart beats as one big muscle. It's one big muscle joined together because of these structures called intercalated discs. It makes the heart one massive muscle. I can't say, hey, heart, I just want to use 25% of you right now. So with the rest of the 75% of you go to sleep. It doesn't work that way. And the reason it's able to do that is because the heart has what's called its own conduction system. And really, to understand that, we want to understand a real basic, what I would call an EKG. So, if you were looking at skeletal muscle, you would do what's called an EMG, electromyogram. I could put some pins in your shoulder into your muscle. If you had MS or ALS, or you had some type of dysplasia, some issue to do with your muscle, I could actually see if you've got conduction issues. You may have had someone tested your tendon reflexes and said your reflexes may be weak. It may be because I'm not conducting electricity through the nerves going to my muscle. But my heart's got something called an EKG. So just remember, skeletal muscle EMG, electromyogram. So just remember, skeletal uses a EMG, which is electromyogram, where a cardiac muscle is going to have its own conduction system, but it's going to have an EKG, electrocardiogram. A lot of people oftentimes ask, well, how come you say EKG and then you just spelled it electrocardiogram? Answer is that electrocardiogram was invented by a guy named Einthoven. He was a Dutch-German physician, and when he did it, he used the German word K, and the German word for heart is cardio, K-A-R-D-I-O, versus cardio, which is our word for heart. So now all we want to do is just look at what I would call two things. We want to look at the conduction system of the heart, and we want to look at a very basic EKG. So let's first of all understand a real basic EKG. To understand an EKG, we've got to understand the concept of polarization and depolarization and repolarization. I mean, we have the same thing in skeletal muscle, but it's just not as complicated. I mean, I can sit here and say, I want to lift this cup right now for the next, let's say that my heart's beating at 72 beats a minute. And I know that you beat 72 beats a minute is a kind of a standard heart rate. And that means that every 0.8 of a second I'm having one of these waveforms. But just think that heart muscle is so organized, because if I told my biceps and triceps that I want to flex and extend 72 beats a minute, 24 hours a day, 7 days a week, 365 days a year, I know that this muscle couldn't do it. It would wear out, it would tetanize. And therefore, that's why the heart uses such a high oxygen demand, and it's able to keep up with that because it's so well organized. So I always think the best way to think about it is number one would be a magnet. So when you were a child, somebody probably gave you a couple of magnets. And so you had these two magnets sitting here. And you said, gee, you know, I took the magnet, it looks like I could flip it around. So if I had the magnet like this, it looks like this is a positive charge here, and this is a negative charge here. And if it was that way, these two things would jump together. So therefore, opposite charges are going to attract. But if I flip these pen around, and I had a positive charge here, and a positive charge here, which is what this is representing, instead of coming together, those two cells would pull, those two bar magnets would come apart. Okay? So if I kind of think of that analogy, there must be some type of a charge on the inside of this bar magnet versus the outside of that bar magnet.